So, we will continue with our discussion on diffusion. Last time we introduced the concepts of fixed laws, right, and we looked at two laws, fixed first law and fixed second law. The first law was with regards to, if you remember, steady state diffusion, and the second law was with regards to where it is not steady state, right, it is dependent on time. The second law is the one which is mostly used, because that is the one which is almost always encountered, right, in real life problems, in biological problems, and that is why you will see that I mean it is kind of omnipresent, it is present everywhere. And so, it is a very fundamental equation to describe any sort of diffusion, right, whether it is particle diffusion, whether it is heat diffusion, or whether it is current flow because of potential gradient. So, that is the fundamental equation we are looking at. So, now what we will do is, last time we had just looked at the diffusion, but we had not included any other forces, which is referred to as an external force. What is the external force? For example, if you are moving in a fluid, you consider yourself to be a particle, then you would always be encountering something known as friction, right. And how can we bring friction in? Now, remember, if you can bring friction in, then the particle is going to diffuse, the particle is also will also be facing friction, right, and in that case there might be a chance for you to develop a relation between the diffusion coefficient and the friction coefficient, is not it, because the particle is experiencing both. One is its intrinsic diffusion coefficient because it is moving around here depending upon its size. The other one is the friction coefficient, which is coming from the viscosity of the solvent where it is diffusing. So, that means there has to be a relation between its diffusion coefficient and the friction coefficient, and that is what we are going to try to develop in the first part of the class, right. So, how do we do it? So, that is where what we would do is, so we would introduce frictional forces and diffusion. Okay. So, what we do is, so for a particle moving in a certain fluid, what I can say is the frictional force or the force which is applied on it due to friction can be written as this. What was the last equation number? Was it 11 last day, right? So, let us use this as 12. Okay. So, this is the force, applied force, right. This one is referred to as xi, it is called the friction coefficient, not frictional, friction coefficient or coefficient of friction, and v, what do you think v is? Velocity, right. So, velocity of the particle. Okay. Now, they are straightforward, so nothing big about it. Now, what we know is, whenever we talk about diffusion, we have learned something which is very fundamental to diffusion, that is what? It is the flux J. So, we have to be able to relate this to our flux J, right. Now, remember, what was your flux J? Your flux J, which we had derived in the previous class, is equal to C times V, was not it? This is from previous class, I have forgotten the equation number, but not worry about it. Okay. So, we know this, we have equation 12. So, what I can now write based on this and equation 12 is, I can replace V by what? F by xi, right. So, that means I can write, now what I can write is, I can write that the J, the flux of the applied force, is equal to C times V, which was F over xi, okay, and say, and this would be equation 13. Good. So, now what you have is, see, the particle is diffusing. So, there is a flux because of diffusion. Now, the particle is experiencing friction. So, now what you have done is, you have introduced an extra flux which is coming because of friction. So, then what is the total flux now? then your total flux J is the total flux would be equal to 1 because of the concentration gradient, is not it, which was minus d dc over d of x, right, and this was one flux which is always there because of the concentration gradient, that is why your particles are diffusing. If there was no concentration gradient, then the particles would not be diffusing in any particular direction, number 1. But then along with this, what do we have? We have C by, right. So, now your flux is made of two components, one is solely because of concentration gradient, Fick's first law, and the other one is because of friction, both will give rise to the flux, right. So, if we have this now, remember we also discussed that your Fick's second law is the one which we should really care about, right, and if we do that, then what we have to calculate is something, what is it, dj over d of x, because remember Fick's second law was what, del c or dc over d of t is equal to minus dj over d of x or del j over del of x. So, if I do that here, and remember I am assuming that d is independent of x, that is what our assumption was when we derived Fick's second law, then I can write this is minus d, this would be d2c dx squared plus f by xi then dc over d of x. Okay, just a simple differentiation with respect to x. Now, we know from before we know that dc over d of t is equal to minus dj d of x. Okay. We have done this in the previous class. So, then see what you have done now is you have actually related your dc over d of t, right. You have related that concentration gradient with respect to time with the gradation of flux, and remember in this case the flux does not only have the diffusion because of concentration gradient, but it also has the friction information involved. So, then if we use this, what we should be getting is dc over d of t is equal to minus d d2c over dx squared plus f by dc d of x. So, this is your dj over d of x and with the negative sign, and therefore, from here it is easy to write that dc of d of t is equal to d d2c dx squared minus f by dc d of x, is not it. So, this is equation number 16 and this is referred to as the Smoluchowski equation. Okay. This is referred to as the Smoluchowski equation. What does this equation do? What this equation does is it relates the diffusion coefficient d with friction coefficient, which is xi. That is why this equation is so important. Okay. Now, since we have come this far, let us go a little further and let us try to develop our relation, an actual relation between your diffusion coefficient and the coefficient of friction, a very simple relation, right. How do we do that? Have you heard of the Einstein-Stokes relationship or the Einstein-Stokes equation? Okay. So, that is what we are going to derive right now. Okay. Just look at this. So, what we do now is take a situation where j is equal to 0. J is equal to 0 means we are looking at an equilibrium situation. What do you mean by equilibrium? At equilibrium, that means this is an equilibrium situation, right? So, if J is equal to 0, that means there is no change of flux, everything is equilibrated. And how do we kind of rationalize that? You just think about this. I have a beaker, say I have a solvent, water, and I put in a particle or multiple particles. Well, let me use a different color for the particles. So, the blue ones are the particles for you. These settle down at the bottom of the beaker. Okay. See, with the particles settle down at the bottom of a beaker, what is the force? The force is gravitational force. Okay. Now, but the moment the particles settle down at the bottom of the beaker, what is happening? The concentration of the particles is maximum where? At the bottom of the beaker, and at the top of the beaker where you have the rest of the fluid or the rest of the solvent, the particle concentration is very low there. So, you have a concentration gradient. Now, the particle after settling down will start moving up, diffuse, because of neutral based on the concentration gradient. So, you have two opposing forces. What are the two opposing forces? One is your gravitational pull, right, which is coming down. So, that means one is, this is two opposing forces, this is gravity, and the other one is your concentration gradient. So, these are the two forces which are acting in opposite directions. So, you can understand at one time these two would balance out each other, and what will happen at the time? J would be equal to 0. That is the situation we are talking about, okay, where these are perfectly balanced, equilibrium situation. Now, if that is the case, what we will do is, because J is equal to 0, and remember J as we defined was minus d dc of d of x plus f by, what was it after this? C, right, because of friction. In this we are using J equal to 0. Okay. If J is equal to 0 now, what do we have? So, what we have is from here, then I can write d dc of over d of x is equal to f by xi c, and let this be equation number 17 for us. I hope that is what it is, right. Yeah. See, now we have a very simple integration. What we have is, what we can do now is, we can do dc over c is equal to f by d xi then d of x. Okay. Now, we will integrate this, but we will include something which you know, it is like this. So, what I will do is, I will write is dc over c is equal to integral f dx over d xi. Now, d is a constant, xi is a constant, both of these will come out, right. So, here what I can write is dc over c. Now, look at this, I will write 1 by d this. Here I will define a term, the term is minus f dx, I will define a term minus f dx, okay, and I will be having a minus here to neutralize this minus sign. Okay. Now, what is integral of f dx? Can someone tell me? Work done, good, right, force times distance is work done, right. And how do you define reversible work? So, a normal PV work is minus P dV, right. and then you integrate. Okay. So, this one we can also do the same thing. So, what we can now write is, therefore, dc over c is equal to what? Minus w d over d xi, where we have defined w is equal to minus f dx, okay, and this w, so this one you can also write as minus f dx, taking the minus sign inside the integral, and w is referred to as the reversible work, and w is referred to as the reversible work. Okay. So, that means you have related this change in concentration gradient to something which is resembling work f dx. Now, if you integrate it now, see, look at the integrals limits rather, this is what? I mean, yeah, this I have already integrated out, x is equal to 0 to x is equal to x, say. So, what I can write now from here what I can write now is, I can write natural log c of x over c where x is equal to 0, because that is what you are integrating it from, right. X is equal to 0 to x is equal to x, that is the total distance the particles are travelling. This would be equal to minus w over d xi, or I can write c of x is equal to c 0 then exponential minus w over d xi, and this would be equation number 18. Is the derivation clear to everybody? Okay. Now, one more thing, because we are at equilibrium, what sort of statistics apply? Because we are at equilibrium, what sort of statistics apply? Starts with a B, Boltzmann statistics, because we are at equilibrium. So, at equilibrium, applying Boltzmann statistics, one can write this, one can write that c of x over c of 0, this should be, well, does not matter, but this should be 0, just make that change, c of 0, it is the same thing, is equal to exponential minus w over d xi, which is from 18, and because we are applying Boltzmann statistics, this should be equal to what? Can someone tell me? exp minus w over kt, because Boltzmann, for Boltzmann everything is defined in terms of thermal fluctuations, which is kt, isn't it? You can only do this because you are at equilibrium and you are using, remember, reversible work, because equilibrium is a signature of what? Reversibility. Okay. So, what does it mean? That means these two should be equal, isn't it? We can easily equate these two, because both of these resemble the same thing, c of x over c of 0, right, one from Boltzmann and one from the one you just derived, having constant flux j equal to 0. Then what can I write from here? Then I can write, if both of these are equal, then I can write d xi would be equal to kt, excellent. Therefore, d is equal to what? Kt over xi, and this would be equation 19. Have you seen this before? That was very fast. So, this is what? This is the relation between what? D, the diffusion coefficient, and xi, the friction coefficient, through a Boltzmann constant, and obviously temperature is there, because temperature will define both diffusion and friction, right. So, what is this equation referred to as? This refers to as the Einstein Smoluchowski equation. This is referred to as the Einstein Smoluchowski equation. Okay. Now, what it means is, if somehow you can calculate the friction coefficient xi, then you immediately know what your d is. That is what it means. Now, the friction coefficient, this is something which you definitely know. So, do not say no now to me. You have heard of Stokes' law, right? For a spherical particle, from Stokes' law, what do we have? The friction coefficient is equal to 6 pi eta and say A or R, does not matter, right. Eta is what? The viscosity. Okay. So, if this is something you know already, then you put it here, use 20 in 19, and this is what you get. D is equal to kT by 6 pi eta A, let this be 21 A, or I can also write, or D is equal to kT over 6 pi eta, sometimes people write as RH and tell you what that means, 21 B. So, this is 21 B, this is 21 B, that is 21 A. So, eta is definitely the viscosity, A is the radius of the sphere, right, and RH, can someone tell me what RH is? RH is hydrodynamic radius. H stands for hydrodynamic, and obviously R is radius. Why do we say hydrodynamic radius? Because when your spherical particle is moving in, say, water, hydration, then your spherical particle, depending upon its charge or whatever, would be hydrated to a certain extent. So, the actual radius you look at is not the particle itself, but along with it some layers of solid molecules, and hence it is called hydrodynamic, because it is a dynamic thing which is moving along with the spherical particle, right. So, this relationship, both of these are referred to as the Stokes Einstein equation, and this is something which is fundamental when you talk about diffusion. Okay. So, this so imagine where you started from. You started from flux, right. There was no friction, you put in friction, then you define equilibrium condition, and you found a very simple relation between d and the friction coefficient. Now, see, this friction coefficient we took was that of a sphere, right, but if you are going to take some other particles which are not spheres, that xi friction coefficient is going to change. So, there are ways to calculate that, you can even look up, right, but once you know xi, because these have been done, once you know xi, then it is very easy for you to estimate what the diffusion coefficient d, right. And if you are talking about diffusion coefficient is an intrinsic property, and that is why it is so important for you to have this relationship in your hands. Okay. Essentially, that is what you just derived. Okay. So, having derived the Stokes Einstein relationship, our next step would be to look at something which is referred to as diffusion controlled reactions. Okay. But I will just not do it right now, I will just hold on to it. In between, just write it down, I will hold on to it. In between, I will do just one more thing. What I will do is, we will actually derive a condition where you have particles diffusing towards a sphere. What do I mean by that? What I mean is, I have a spherical particle, right, of a certain mass. This is my spherical particle, and then I have very small particles which will come and diffuse and interact with the central particle. Now, this particle, because we are talking about biophysical chemistry, this particle can be your protein molecule. And you can understand the assumption here is that your protein molecule is much bigger than the particles, all of these are considered spherical, which are diffusing towards the protein molecule. So, these small ones can be, say, certain small ligands. So, if you think about an enzyme catalysis, what will happen? The substrate has to diffuse towards the enzyme. So, the enzyme is a protein, and the substrate, which is, say, a small molecule, is essentially, that is what you are looking at as the dots surrounding the spherical particle. Okay. Now, how do you develop the idea behind this? How do you actually look at it? Because we are talking about a spherical particle diffusion, what we do is we use spherical polar coordinates. That is number 1. If you remember, we had used spherical polar coordinates once before too. Where did we use it? Okay, that was two before in this class. It is very typal one. We went further. Remember Poisson equation? We used that. Yeah, hydrogen atom we definitely did that, but I did not do it with you, right? Okay. What we also take into consideration is, we know this equation del C over del of T is equal to d. We know this equation, right? We are considering motion in spherical polar coordinates. So, x would be replaced by r, okay. That is number 1. Number 2 is, we will apply steady state condition for simplicity, okay. We will apply steady state condition for simplicity. What do you have at steady state? How do you define steady state? So, in this equation, if I assume a steady state condition, what will happen? Del C by del T should be equal to 0, that is a steady state condition, right. To simplify the problem, that is what you are assuming. So, what you can write now is, x will be replaced by r, because you are talking about spherical polar coordinates, right, and del C by del T is equal to 0. This is your steady state assumption. Also, we are only looking at diffusion involving radial coordinates, no angular dependence is involved. Please keep this in mind. We are considering diffusion involving radial coordinates without any angular dependence. That means, in your full form of your spherical polar coordinate, the theta and phi terms, they vanish. The only one you left with is the radial term, the first term, if that is a radial term. So, then the way our equation simplifies is, if it is del square C, where del square now is only a function of a radial coordinate, this can be written as 1 by r d2 r c over dr square, and this is equal to 0, and this would be equation 22. So, this is the equation we are trying to solve. Okay. So, please remember what you are actually trying to do is, if you have a big protein particle and if you have diffusing ligands coming in, you are trying to solve essentially the diffusion equation using a steady state assumption. That is the simplest way to look at it. Now, if you try to solve this, the equation 22 can be written as d2 RC over dr square is equal to 0. I multiply throughout by r cancels out, means it doesn't is not there. Now, what I do is I integrate it, I do a integration, I do a first integration, because you understand I am at the double derivative, right. So, if you have to go to the solution, I will have to do at least how many integrations, 2, right. So, if I do the first integration, then can I get this d of r c d of r is equal to say a constant a 1. Right. Look at the validity of this. Why? If you look at this, if you are going to apply integration, if you are going to apply differentiation, that means if you are going to take d of r of these, what will you get? D of r on this side would give you this one, but this is a constant. So, this one would give you what? 0. Okay, good. So, a 1 is your first integration constant. Good. Now, we integrate again, we do the second integration, right. So, what we have now is we have d of r c, okay, is equal to now a 1 dr, that is what we have now. So, this is your second integration, okay. So, if that is what you have, then you have r c is equal to what will you have now? You will have a 1 r, but another constant plus a 2. This is the second constant of integration, right. This would be 25, a 2 is your second constant of integration, or I can write c is equal to a 1 plus a 2 over r, this is 26. A 1 and A 2 being constants. Now, you will realize you have one equation which depends where concentration is dependent upon r. So, I can write this as C of r, right, I can write this as C of r just to be mathematically rigorous. A 1 and A 2 are two constants, but I have one equation. So, I will need how many? I will need two boundary conditions, is not it? Only if I have two boundary conditions will I be able to solve for both the two constants A 1 and A 2. Hence, to get A 1, A 2 need two boundary conditions. Okay. Now, what are the two boundary conditions? Let us look at the boundary conditions. The first one, what happens if r tends to infinity? What happens if r tends to infinity? That means if you are here and this ligand is at infinite distance away from the sphere, that is what you are looking at. If that is what is going to happen, then I can say at C r tends to infinity can be considered to be C naught. This is the normal concentration of the diffusing particles, okay, at r tends to infinity, because it is so far away, you are just getting the normal bulk concentration, it is not influenced by the particle which is in the center, the big spherical particle. Okay. So, if that is the case, now we go back to our equation, C of r is equal to a1 plus a2 over r, where r tends to infinity. If r is tending to infinity, then Cr tends to what? Cr tends to C naught, right, at r is equal to infinity. So, this means this is also tending to infinity. So, right. So, that means I can write C naught is equal to a1 . So, you already have one constant of integration, right, good, but we need what? A2. Now, for A2, this is what we assume. For A2, what we assume is, if this is your particle and if this is the diffusing species which is coming to your particle, it comes here, the moment it strikes here, the particle, the small one I mean, is instantly absorbed by some process. Instantly absorbed by some process. What does it mean? That means the moment the particle, say the moment the substrate comes to enzyme, it immediately what happens? It immediately reacts. Okay, it is an immediate transformation. So, there is no time lag. So, this is an assumption, remember. So, that means what can we say about the concentration of the particle? The concentration of the particle at say r is equal to a, where a is the radius of the big sphere, what would the concentration be? 0, isn't it? Because the moment the particle comes in, it is instantly eaten up. Okay. So, that means if r is equal to a, where a is radius of the bigger sphere, then C of A is equal to 0. C of A is equal to 0. And if we use this in a previous equation, so what we have now is, I have C of r is equal to, what we had was a1 plus a2 over r. We already know what is a1, C naught. We know that when r tends to a, then C of a tends to 0. Okay. And this, then we can write from here, C of a is equal to C naught plus a2 over a, when r is equal to a. Now, we already know that this is 0, isn't it? Therefore, 0 is equal to C naught plus a2 over a. Okay. So, what we have is, so what is a2 equal to? What is a2 equal to? Minus C naught a. So, that means you have your second constant of integration. Good. See, it is a constant. So, it has to be related by constants, and the two constants are C naught and a, both of these are constants, right. So, then what does the final equation now become? The final equation becomes C of r is equal to C naught minus C naught a by r, or C of r is equal to C naught 1 minus a over r, and this would be, what is the number? 26, 27. This is 27. Okay. So, what you have is, you instantly have a relation now between C of r, C naught a, which is the radius of the bigger sphere, and r. Okay. So, how will it look like? Remember, we will finally go for the flux. So, I will come to that, but how will it look like? What it will look like is this. If I try to plot a curve, right, like this, if this is the center of the bigger sphere, okay, if this is the center of the bigger sphere, and say this one is A, where A is the radius of the bigger sphere, okay. Say this is in this direction, this is C of r, okay. What is the maximum value of C of r? C naught. So, I can put in C of naught here. What is the minimum value? 0, right. Remember, this is your r. So, at here, so this is your 0, at here you can see your plot will look something like this. So, it would be 0 at r is equal to A, but then it will gradually rise based on the equation we just derived, and finally max out at r is equal to infinity, which is C is equal to C naught. See, it is very simple to understand, right. I mean, that is what is going to happen. It is going to be absolutely depleted, that is C is equal to 0 in the proximity of the sphere, and then it goes on increasing. Okay. But how do we define flux? Remember, we are always talking about flux, always talking about flux. How did we define flux? Remember, what was flux equal to? Flux is equal to minus d, then dc of d of x. Here I can write dc of d of r. I have to find flux. Okay. Now, based on the equation we just derived, based on the equation that C of r is equal to C naught 1 minus A by r, okay, this is the equation we have just derived, equation number 27. Then if I am going to calculate J based on this, J would be equal to minus d C of r over d of r. So, that means d of r C 0 1 minus A over r. Okay. Now, if you look at the differentiation now, whatever the first term, what are the first term? It is d C naught over d of r. It should be what? It should be 0. C naught is a constant. Okay. Then you have a negative sign. This negative sign cancels out here, but you have 1 by r. So, another negative sign comes in. So, this then J would be equal to minus d C naught A over r square, d C naught A over r squared, right, and this is number 28. See, what have we just done? You figured out the variation of concentration as a function of distance based on this model, a simple model. Now, what you are doing is, because you know that once I have the concentration gradient dc or d of r, I can always relate it to what? My flux of the particles. That is what we just did. See, everything is very logical. Now, if you have that, one prime question that always comes to our mind is how many collisions we have per second, because finally the reaction would be defined by what? The number of collisions we have, right. That is why when you increase your temperature, in most cases the reaction rate increases, because obviously increase the collision rate. So, then how would you find your collision flux or collision rate or collision current, as I will define? So, what we will now define is something known as I of A. We will define something known as a collision current, which is I of A, I standing for current, A stands for the radius of the sphere. How did we define flux? If you remember, flux was the number of particles flowing through per unit area per unit time. I am trying to look at the number of collisions per second. That means I already have per unit time there, because it is per collisions per second, but I need the number of collisions. So, what do I need to do? I need to take the flux and multiply it by what? Area, because this is not collision per unit area. What I am trying to get is the collision over the whole area, and collisions is the number of collisions per second. That is what I am trying to calculate. Your flux is defined as the number of particles, if you remember, that C A delta x over A times delta t. Delta t is your per second, So, if I have to get the total number of collisions, I have to multiply your flux by the surface area, that is what you have to do. If you do that, so that means I of A would be equal to, so it is given out here, J calculated at r is equal to A, because A is the radius of the sphere where the particles come in and diffuse and react, times area, but what area should we be considering now? Surface area of what? The sphere. What is the surface area of sphere? 4 pi r square, in this case it would be 4 pi a squared. We have already derived what J of A is for us. Okay. So, and this therefore I of A is equal to minus d C naught A by A square, where r is equal to A, right, times 4 pi A squared, or I of A is equal to minus 4 pi d C naught into A, and this would be equation number 29. Have you seen a form of this equation before? When you did kinetics, you never looked at diffusion control reaction, you never looked at something known as this Smoluchowski's diffusion control limit. Your faces tell me no. Okay, I will not ask you anything more. Okay, if this is the collision current, then the association rate is often defined as, it can also, I can this can often be defined as minus k times C. Okay, minus k times C, there is your association rate. Now, please keep in mind there is a negative sign out there, but do you understand what the negative sign means? The negative sign means, see, your r is increasing. If this is your sphere, where the ligands are going to come and diffuse, your r is increasing in that direction, but the concentration gradient of the ligands is in which direction? The other way, right? That is what the significance of the negative sign is, because if your concentration gradient is not the other way, then you will never be having a reaction, they will never interact, right? You have to have a reverse concentration gradient, like that is what the negative sign denotes. Yeah, simple. So, if you compare, so if this is 30 and if you compare these two, what do you get? What you get is, I define something which is k is equal to 4 pi d A, and I name it as Ka. And this I say is 31. Okay. This is the rate constant. Can someone tell me what is the significance of this rate constant? You are talking about a reaction between two molecules, that means it is essentially a bimolecular reaction, but you know that every collision would not give rise to a reaction. Why? Because you have an activation energy to go through as defined by Arrhenius. So, if for the sake of argument you consider your activation energy E of A to be 0, that means there is no activation energy, then wouldn't the rate constant you get there be the upper limit of your rate constant or of your rate? That means your reaction is only what? Controlled by what? Diffusion. That means it is only controlled by encounter rate, there is no information of activation energy involved now, and because you are not involving any activation energy, this is the highest you can go to. So, this is what your upper limit is. Now, if you have any other things coming in like activation energy or any other stuff, then what will happen? Your rate will only decrease, it can never go beyond this. Why? Because you have already defined it as your diffusion control limit. You cannot be having anything which is faster than your diffusion control, that is what the bottom line is. because for reactions you need to have collisions, for collisions you need to have diffusion, and once you have defined diffusion, then that means the rate at which they diffuse is the fastest rate at which you can have a reaction, based on the assumption that your activation energy is what? 0. So, if you put in other stuff, other barriers, activation barriers, then your rate can only go down. Hence, this is called Smoluchowski's diffusion controlled limit. This is called Smoluchowski's diffusion controlled limit. Now, I hope you understand. Remember, I wrote this thing down and I said I will come back to it. I wrote this as diffusion controlled reactions. So, what do I mean by diffusion controlled reactions now? That means activation energy E A is assumed to be 0 and your reaction rate is solely defined by the encounter rate, okay, by the encounter rate of the diffusing species. Is it clear to everybody what we mean by diffusion controlled reaction? And there was one condition we used. The condition was that the moment the particle comes to the sphere, it is instantly absorbed. So, it is called the absorbing condition. I will not write it down, it is called the absorbing condition or absorbing boundary condition. That means, the moment it hits the boundary, it gets absorbed. Okay. So, what is the importance? Where would you use this? If someone would ask you what is the maximum rate at which the reaction can happen, what is your answer? This is your answer. This is your diffusion limit, right? You cannot have it faster than this. It is always defined by what? D, the diffusion coefficient, and obviously you have A, which is the radius of the sphere. Now, just before ending the class, I will just extend this a little more and say what we up till now we had considered is the protein is a big one and the particles are diffusing. That means, protein is essentially immobile with respect to the diffusing particles. Now, what happens if I have a case where I have the protein and my particles are also decently sized? That means, I am looking say at an interaction between two proteins, not necessarily an enzyme and a ligand. I can look at protein A and protein B, right. So, this means I can look at protein A, I can look at protein B. So, in this case what will happen is, when we talked about the previous problem, what did we talk about? We talked about only A. What was A? A was the radius of the sphere A, is not it? But here you consider this to be hard spheres. I have this one would be what, say radius of molecule A, right, and this one should be what, radius of the protein B. Okay. So, then when I defined K of A from before to be 4 pi d then A, now I am doing a transformation. I am doing a transformation saying that because both of the things are diffusing, I will write this A as R naught, where R naught will be equal to what? Tell me, A of A plus A of B, is not it? Because now protein B is not small with respect to protein A, okay. And because both of these are diffusing, remember when these come together like this, what happens to the relative motion? additive, isn't it? So, then I can define d to be d of A plus d of B. Now, also, well, okay, also comes later, but let me write this down now. Then k r 0 would be equal to 4 pi, right. A would be replaced by what? R 0. Then I would be having d of A plus d of B, isn't it? So, this is one of the most general expressions for the rate constant you can have, okay. And now putting this in the actual equation, remember we derived I of A is equal to minus K A times C, this is what we were saying, right. So, here I of R 0 would be minus, I already know what K of R 0 is, K of R 0 is what? 4 pi R naught d of A plus d of B. Now, this is logical to assume in the previous case when we said minus K A times C, which one was moving? Only the small particle is moving. So, we had only that concentration. Now, both the particles are moving. So, we can write C A naught times C B naught, because it depends upon the concentration of both the particles. Okay. So, if you ever look up your textbooks, any textbook, or if you give it a search on Google for Smoluchevsky's diffusion limited rate constant, this is what you are going to arrive at, a form of this. Okay. And keep in mind, we have done this for molecules, that means molecules, one molecule, one protein molecule A, one protein molecule B, and so on. That means this concentration is essentially in terms of molecules. If we have to go to moles, what will happen? You have to multiply it by the corresponding Avogadro number. So, I will give you the most general equation in the next class, but if you would look at this equation, you would see that it would only differ by another constant, which is say the Avogadro's number. Okay. It just takes into account that you have a mole of molecules which are diffusing and reacting with each other. Okay. So, this is a very important equation again. Please keep this in mind whenever you talk about diffusion, or in other words, if ever you are going to ask or going to be asked what is my diffusion controlled rate, this is what people are referring to. That means, whenever diffusion is happening, whenever collision is happening, you are having a reaction, there is no activation period, that is your higher limit, always the upper limit. Okay. So, next class I will give you a more general equation for this one, I will take into account the Avogadro number and some volume units I will show, and after that I will go into a form of equation which is again a very important equation, all of you should be knowing. It is referred to as the Langevin equation, which takes into account your Brownian motion. For example, if you would want to define the movement of a particle experiencing Brownian motion, what sort of a motion is Brownian motion? Random motion, right? So, random motion is defined by a randomly fluctuating force, and if you take a randomly fluctuating force, time dependent, then over a long period of time the fluctuation average of the fluctuation force would be essentially equal to 0. Why? Because it is fluctuating in every direction, it is a random force, right. And obviously, for a Brownian particle it is going to experience this random motion, it is also going to experience one more thing. What is that? Friction. So, Langevin's equation describes, it is a Newton's law essentially, it describes the acceleration of the force of the particle being equal to or being composed of two things. One is your random fluctuating force for the Brownian motion, and the other one is the one which retards its motion, which is your diffusion motion, which should be acting in the opposite direction, and you will see the sign conventions will be maintained there. Okay. From there we will go on to something known as correlation function, and I will just give an idea of what correlation function means. Okay.